want to begin by introducing what I think is the fundamental problem of cognitive science in the 21st century, and it's the problem of common sense reasoning. Right now I'm violating your common sense reasoning, and I'm violating it in a particularly trivial way. There's nothing physically impossible about studying a lecture from the back of the class. There's nothing logically impossible about doing it. But by messing with your common sense reasoning, the kind of knowledge you may not know that you have until it's violated, I mess with all kinds of things. Their ability to hear me across in the next section, your ability to categorize me, your ability to make predictions and explanations, even your basic ability to orient your attention. This is a really, really fundamental set of background knowledge, ideas, assumptions that you carry around with you. And I think it is one of the super hard, complicated, central problems of intelligence. A causal problem we routinely underestimate. Most of you are familiar with this gentleman, this is Alan Turing. He brought us computers, right? He also brought us a very important test of intelligence that most of you here are familiar with, the idea of the Turing test. The idea that one way to know if you had succeeded in really understanding and engineering intelligence would be if you could design a computer that could fool a person into thinking it was a person. The Turing test, as many of you know, was the idea that you would have a person back here and a computer back here and someone out here who was typing questions and getting answers back. And if the person really couldn't tell which was which, then you could justifiably say that you'd achieved something like artificial intelligence. And what Alan Turing believed was that this was a pretty tractable problem. In 1950, he thought that 14 years ago we would have nailed this problem. That computers, people would, by about 70% likely to make the right identification. Okay? And as we know, we're still facing that problem. Martin Minsky was similarly optimistic because within a generation, the problem of creating artificial intelligence will be substantially solved. And a few years later, he said this is one of the hardest problems ever undertaken. Okay. There's a reason why we're devoting a whole wood full of that. Now, as many of you may also know, no computer has yet passed the Turing test, right? None has been reliably confused with a human being. So what we think of now is something called the Loebner Prize, which is the computer that does the best job, right? It's never actually confused with a person, but it does better than all the other computers. Let me show you what some of the recent winners look like and why they don't actually confuse interrogators about their humanness. Here's a little transcript from a winner of the prize. So you read, yes, what's your favorite novel? There's no such thing, meaning you don't have a favorite novel, or novels don't exist. No, what's your favorite book then? Are you serious, etc. Okay? Here's another recent winner. Do you have a pet? No, but I like cats very much. Why don't you have a pet? Do I need one? I think you do? I think I do. Well, then get one by God. Good reasoning. Where can I get one by God? Yeah, it's interesting that we haven't solved this problem because Freud wanted to engineer common sense reasoning. Well, how would you do it? And one instance, people have given us, well, poor computers, right? Like we have all this time to live in the world, you have bodies, you have all this information pouring in, and computers just have what we tell them. And maybe they just don't know enough, right? They don't know what. Let's just give it a lot more facts about the world. And you might be troubled by this, right? Because facts seem somewhat uncountable. Suppose I want to know that Barack Obama is in Washington, and now I want to know if his spleen is in Washington, or his right toe is in Washington, or his second toe, or his third toe, or any innumerable facts about him. The philosopher Bert Dreyfus, who was on my dissertation committee at Berkeley, was deeply skeptical. He said if you got all that knowledge into a computer, you wouldn't know how to retrieve them. Right? It would just be a bunch of things. There's reason now to suppose that Bert Dreyfus was wrong. Right? Many of you may have heard of this. Let's see if it plays. This is my test to see if all of my live links play. Wow.
No, the other panel is already there. You go to the other tabs there.
Next tab. So many.
I'm really not sponsored by these folks. All right, here we go. Jeopardy. Many of you hopefully saw this, right? Can I just see a show of hands if you watched Watson beat our best Jeopardy champion? Great. I'm going to go in a little bit of the way. Let's see, I actually put the time on there. I think it's right there.
Again, the art in steel for $1,600. In May of 2010, 5 paintings worth $125 million by Brock, Matisse, and 3 others left Paris's Museum of this art period.
1648. Let's see if I can get back.
What is Picasso? No. Wait. Then.
Oh, Remit.
What is Cubism? No.
That's for the people. What I really want to show you is 2 seconds later here, because I want to focus on this.
Same amount, but Watson retains control of the board.
He's killing everyone, right? He's killing the best team.
Answer. Hedgehogs are covered with quills and spines, which are hollow hairs made stiff by this protein. Gotcha. What is carrot?
I want you to see what he gets right, but I also want you to see what his next best guesses are. Because that is where I want to stop. Watson was a remarkable success. Watson handled natural language processing. Watson beat our best Jeopardy players. Joseph's problem is a hard problem. It turns out that this computer was able to understand natural language, take access to an enormous amount of facts, and spit it out in real time faster than human competitors, right? So we can solve that problem. But he solves it in an interesting way. And the hard problem may be that this kind of knowledge, right, the ability to access all that world knowledge is neither necessary nor sufficient for passing the test. Right? You can have access to all this information and not be recognizably human. And that is partly because it is not recognizably human to make an error of this kind. Right? You may not know that keratin is what hedgehogs' spines are made of, but you surely know that porcupine isn't even in the ballpark of the kind of answer that you should give. Right? It's related, it's a relevant fact, but it's not an answer to that question. You structure your knowledge and your representations differently. You may not have as much of it, but it's not organized like this. Now I want to present a contrast. I want to present a kind of organism that not only passes the Turing test, it solves all the hard problems of cognitive science. It solves problems of motor planning, of causal reasoning, of number understanding, of spatial navigation, of theory of mind, of natural language acquisition, of moral reasoning. It does all of this in unsupervised learning. We supervise the organism, but not the learning, in parallel in a few years of life, and that is young children. There are a lot of things young children don't do. They're not going to be allowed to drive cars. We'll have self-driving cars. We're not going to have 4-year-olds driving cars. Young children are really bad at tests. They're extremely bad at Jeopardy. They can't even remember to ask the questions in the form of a question, right? But young children can answer this, and this, and this, and this, that you needed to know to pass the Turing test you learned before kindergarten. They have structured knowledge. They have structured representation. If you put them behind there, you might not mistake them for a grown-up, but nor would you mistake them for a computer, right? They would answer like a human being. I think this is the deep mystery of human intelligence, what goes on in the very early years of life. Again, the kind of things that are effortless for our children are exactly the kinds of things we don't have the AI and machine learning tools to solve, and that's, of course, the challenge we want to hand back to you all today. Why can our computers play Jeopardy that they can't parse natural scene and tell you what's going on and what the goals and what the people are and what's probably happening and answer infinitely many generative questions about it sensibly, even if inaccurate. Right? The answers may be wrong, but they are reasonable. Okay, so understanding common sense. That's the hard problem of cognitive science. To understand that problem, to solve that problem, we're going to need to understand 2 kinds of things. We're going to need to understand the structure of children's early representations, what they have very early on, and we're going to need to understand the processes for instance of learning. And the way I understand we're going to organize this course is that today I'm going to talk a little bit about the structure of the early representation, and we're going to talk more on Friday about the processes of learning in order to try to get a handle on it. Okay, so my job today is I think, not a very enviable one. So I need to come up with the structure of children's early representation across the whole span of Commonsense knowledge in the next hour or so. this is going to be extremely haphazard. I'm going to apologize for that in advance. What I want to do is give you a feel for the fact that they exist, that there are rich, structured representations very early on. Some of that knowledge is plausibly innate. Other of that knowledge is clearly early developing, early learned. People talk about it as being structured like a theory. Children have abstract, coherent, causal knowledge that supports prediction, categorization, explanation, intervention, counterfactual reasoning in all the ways that our theories do. And it's the structure of those representations that matter. Okay? So I'm going to try to give you some of the highlights, sort of best of empirical data from developmental technology to show a little bit of each of these areas. And then I'm just going to very briefly foreshadow the talk on Friday about learning. And please, nothing less than me getting through all this material. Stop me. In fact, I've already got a number. We're not going to talk about number today at all. So we're just going to do I'm going to talk very quickly about causality, just a few points to lead into Josh there. But please stop me and interrupt, because I'd rather you understand some things well than a lot of things not at all. Let's talk about the object mystery. Because one of the problems here is to make it clear why common sense knowledge is a problem, and as I said, you only recognize it when it's violated. So why are objects a problem? Well, they're a problem because sensory input is continuous. If you look around this room, you may think that you see objects, and you may think that you see agents, but of course you don't. You see a whole bunch of color and texture and shape and form, and you divide it, your mind divided into objects. We operate on these individuals, we count them, we name them, we manipulate them, we represent spatial and causal relations. They're a fundamental unit of thought. And you also have a lot of social evaluation of them, right? This is your computer, not his computer. Your cup of coffee, not his. So how do we get there? And especially, what did you have if I could take you back in time, some 20, 30, etc. years ago? Okay. Well, it was Dr. Garfield, who actually laid out a lot of this problem, a lot of this space. And said we need to understand, if we're going to understand cognition, we need to understand how children understand objects, agents, causality, morality, and space. Said babies, we're going to start with what people assume through generations, which is babies are blank slate. They don't start with very much at all. They have to build it all up from the ground up, right? And in particular, he said babies don't have an object conscience. They can represent what is immediately accessible to their sensory motor system, but when it goes out of sight, it is out of mind. And he had a lot of good evidence for this. In particular, this is you can try this at home, find a baby, hand that baby a really exciting toy rattle, the baby will be enthralled, remove the rattle from the baby's sight, and if the baby is 6 months or less, it will be on trouble. When you bring it back, it's just as excited, but when it goes away, the baby will simply look at you. If the baby's old enough to start reaching or searching, if you hide the object, the baby may look at it, but if you keep hiding it in that place and then in front of the baby, move it to another place, the baby will keep going back to the initial place where it was hidden. It's not going to go ahead and search to where you moved it. It's not going to represent the transformation. And Piaget said this because babies have a very unstable ability to represent abstraction at all. They can't have a representation of something that's not immediately accessible to the sensory motor. You may have heard of this. You may have heard baby black object is permanent. It's still taught in preschools and in early childhood education programs all over the country. It's false. It's patently false. And we have a lot of reasons to think it's false. But nonetheless, Piaget experiments the whole. So I want to talk a little bit about both parts of that. Why do we know it's false? Why do we think that babies actually have very early abstract representations of objects? And by the way, not just babies, all kinds of animals. Chicks do it too. Control weird chicks raised in the dark. You can hatch them and you can show that they represent objects and they represent them when they're out of the sight also. Why do we know about babies? So work in the 80s by René Barjon, I think really elegantly illustrates it. I'm going to drop down to show you these studies here. Okay. What you're seeing on the screen here is what's called a habituation event. You're seeing it at a funny angle here. What you're supposed to be seeing is something like, can I just draw this? I promise I'm not going to do anything. A drawbridge going back and forth like this, okay? It's going all the way down and all the way up like that. You're seeing the side view. So babies are sitting here, and they're watching this. And a habituation event means it's an event that eventually bores the baby. They see this so often, again and again and again and again and again, that whatever their looking time on the first 3 trials was, that average drops in half by the end of their 3 trials. You say they're bored, right? They're no longer interested in that event. They've seen it a lot. Now all you're going to do with the baby is introduce something like an object that is behind this drawbridge right here, a block. And you're going to show them one of 2 things. Either exactly the same event they just got bored by seeing, right? They're going to see that bridge collapse right on top of that object and squish it down. Now that's not possible if there's an object back there. If you know about objects, it's got to stop. One solid object's going to stop another solid object, right? Babies have just been bored by this event. They've seen it a lot. But this event is impossible if they're representing a hidden object. You would expect them to recover interest. You would expect them to look longer, even though this is this familiar event, familiar boring event. This is a novel event. They've never seen that drawbridge stop halfway. But if you represent a hidden object, that is the expected event. That is what you should imagine is going to happen to that object. And what Renee found, and many, many, many people since, is that infants indeed do have abstract representations of objects. They do expect the drawbridge to stop when there's an object hidden back there. Not only that, they're extremely good at estimating about when that drawbridge should stop, how many degrees of rotation that drawbridge should be able to take. If you hand the babies an object first and let them play with it, they can find out that object is extremely rigid, or it's like a sponge and it's a little bit squishy, and they adjust their expectations accordingly. So they can use their own first-hand knowledge of the object property to represent those properties when that object is entirely out of sight. This is a fairly rich representation of objects and their properties in 3-month-old babies. And again, we can now show that even in brand new or newly hatched chicks. So there's something quite rich and structured about the early representation. Here we need to pause and say, why did Piaget get it wrong? Right? Boundary Raphael is brilliant. Thousands of manuscripts, monographs, and books, and like I say, you try this at home with any baby, and you're going to also believe baby's black object permanent. The short answer is there's a lot of challenges in developmental psychology with performance competence distinctions. In this case, there are several fairly simple ones. So recognizing that something has disappeared is easier than figuring out what to do about it. I frequently find myself searching repeatedly in the same place, for instance, for my keys, even when I have just looked there, because I don't really know where else to search, right? And I know it's disappeared, I know it's actually not there, and yet figuring out a plan of action can be challenging. And in particular, we know with babies that very subtle things can affect their ability to search. So as Sayaman showed, that if you have babies who've been searching repeatedly in one location, and then you move the object to the new location, if you let the babies, you shift their posture, and then put them back down, they do a much better job at executing the new reach if their posture's been changed than if they continue in the same posture, right? So some of it is just a motor separation. Adele Diamond showed this quite beautifully related to prefrontal cortical maturation. Babies have trouble inhibiting a reach to the same place and switching it. It's not a conceptual representation. In other words, probably at stake here. It's a performance. It's a performance measure. And you can imagine this yourself when, although you can presumably represent the position of that tennis ball moving forward towards you, you sometimes miss when you are swinging your racket at it. It's hard to adjust your performance to this representation. Okay. So, babies know that objects are back there. They know something about their properties. But what is an object for a baby anyhow? What are its core properties without which it wouldn't be an object at all? This is a question that Liz Spelke, who's a member of this intelligence initiative, really changed, I think, the view of the field and really much of what we know about infancy by taking on. And in particular, she investigated quite early in the 80s some proposed constraints on what you might know about objects that you might need to have in your structure of representation. In particular, she proposed that it's absolutely core to the fact that something is an object at all that you have continuity, right? If I'm going to toss something across the room, you expect it to go in a complete trajectory all the way to the back of the room. You don't expect it to start here, have an empty space between, and end up at the blackboard. Right, things don't just jump over holes in space. There aren't wormholes in the physical world. There aren't wormholes in infant intuitive theory of the physical world. She also said you should understand the objects are solid. That drawbridge study, you don't expect 2 objects to occupy the same path at the same time. But she didn't propose that babies know everything. particular, she thought babies are not likely to know about gravity, they're not likely to know about inertia. And the argument on which she based these is an interesting one. She based it in an argument essentially from error. She said that adults never make errors about continuity. They never make errors expecting objects to pass through one another. But adults are not very good at judging what's going to happen to balls that you drop from moving trains. Adults, as you may know from some studies of intuitive physics, are inclined to think that if a ball is going round and round in a tube like this, they're a little bit uncertain about what physical trajectory that ball is going to take when it pops out of the tube. That's something that doesn't apply to everyone here. I'm going to teach students, but naive adults can get confused in these kinds of cases in a way that they never get confused about these kinds of problems.
No, that core means either genes or not.
Core, in their sense, means a ontogenetically old and phylogenetically early representation that remains persistent throughout development. Even if you elaborate it, even if you get new knowledge, even if it contradicts, you will see the signature of it through. It depends arguably on evolutionary typical experience, right? Like if you do neglect or deprivation, it might not develop, but it's triggering, it's perceptual triggering. So in environmentally normal conditions, you would expect that knowledge to be present, and they have a good evidence again for it. So there are signatures that classically in foreknowledge is that you can find it in other species, you can find it extremely early, and you can find signatures of it in adults who know that, right? In some ways, who should have richer knowledge or even knowledge that contradicts core knowledge. In some ways, you should still find signatures of the early. Okay. So she then went out to test these beliefs and see if she could find evidence that even very young infants had this kind of knowledge. So again, I'll show you a little animation here. Here again, it's a familiarization where you see this is an occluder that drops down. Sorry, let me try to show you just one thing at a time. It's actually, I can't do that. Oh, pay no attention to the curtain. There's a wall that drops down, a ball that falls behind it, right? So again and again, they see the ball fall all the way to the ground, just like balls do, right? And now she's going to test the solidity violation, and where you either see a novel end state, right? The ball never ended up here, and yet you would, of course, expect it to, right? If objects are solid, if they don't pass through things, they move on a continuous path, the ball has to end up here. Or you should have a familiar end state, where the ball drops all the way to the ground, right? Which is just what they've been bored by seeing, that in this context, they should recover interest, they should live longer. And so as a kind of sketch of what you expect data from this to look like, you see the baby's initially interested in the familiarization event, they get bored to that event, and then you show them the consistent event or the inconsistent event. Both are new with respect to that, little bench being there, but one is, although superficially more familiar to familiarization, in fact, a violation if babies have this representation, if they understand that it's part of the representation. And that's what she said. So, what she also found is that in very similar events, superficially quite similar events, babies didn't show this kind of pattern of behavior, right? So it seems equally obvious to us that this is a violation, to have a ball flop in midair, right? Like that does not happen unless you happen to be holding the ball. But an unsupported object doesn't drop and flop in midair. That's a violation of gravity. It's a violation of inertia. Once that object is in motion, if nothing stops it moving, here in our intuitive physics, we expect that thing not to just pause in midair. We don't expect objects to slowly change trajectories. Babies didn't care. Babies didn't care. They were looked equally long at these events. They didn't distinguish the testing control conditions. Similarly, with violations of gravity, if you have that ball roll across a plane, if you put a gap in the plane, this is certainly possible. It can roll under the gap when it's supported by this surface. It's totally impossible that it should do that, but the babies didn't care, right? They were different to do. And René Bayer-Jean, following up on these kinds of studies, went on to develop type ideas about how babies would gradually begin to develop an understanding of what the constraints are in support relations on objects. They know they're solid, they know they're not passed through walls, but it takes time for babies to appreciate not just the objects need to be supported, but the kind of support they typically need. So at 6.5 months, babies are perfectly happy 5 months, babies are perfectly happy to accept the objects need support, but they're indifferent to where on the object that support comes from. To understand why that's not crazy, look around this room and you'll see any number of objects are actually affixed by vertical support, like that clock over there, right? So they have lots of evidence that, maybe it's possible, maybe objects can be supported in other ways. Then they recognize that the support should be underneath, but they don't really care about how much of the supporting surface there is. And it is relatively late in development that they begin to really understand the relationship between the mass of the object and the distribution of that to the supporting surface. And all of this, as Renee points out, goes along with babies' active experience of the world. The fact that they are, at 6 months, starting to be able to reach and manipulate objects in a competent way. They can sit up now. They can move things around themselves. They can experiment with stacking and with sorting and get this kind of information. But they don't need that information to know that objects are solid. They don't need to know it that objects are computers. That isn't the point.
What is the with animals? What is it known about?
Strikingly consistent. Right, strikingly. Again,
What kinds of animals?
The ones that I think make Liz Spelke the happiest are control rear chicks, because you can actually take a chick and ensure that they don't get any visual experience, right? They can hatch right out of the egg, and then you can subject them to habituation experiments, much like this. You can actually get chicks to selectively, I'm going to show you one other thing about Spelke objects when I talk about causality, and you can get newly hatched chicks to selectively imprint on things that they might classify as things that move independently as opposed to being caused to move by other objects. So I think it's the newborn chick studies that are going to do this. But if you think about it, we have lots of social animals, right? There are birds that hatch and fly. There are gazelles that are born and gallop, and mountain goats that go up mountains. It would be hard to do that if we didn't have some sense of how you might build in innate constraints on what the physical world was really like. Okay. Skip number. Yes.
I have this is probably a pretty dumb question here, but so these experiments, are they done on a computer, or do you have sort of illusion that's mocked up to show them like?
These are usually actually puppet shows. So most of these experiments have been done live with real objects in front of real babies.
Does it matter if you do it on a computer instead? You're going to change things significantly?
I'm sorry?
If you do everything on a computer screen instead, will that change the results?
I believe that actually the ones on chicks have been done on computer screens, right, on the chickens. So many of these things have been switched across different times, kind of modality. The main thing is you tend to depress infants looking overall if they're not looking at real world objects. They're actually more interested in real world objects often than screens, depending on the stimuli. So since you want to get as much variability as you can, you try to give them the richest stimuli you can. That may be changing as our computer animations get better. Particularly as developmental psychologists, computer animation skills get better. Okay, let's talk about causal reasoning. If you spend any time around babies or shopping for baby gifts, you can find all kinds of toys like this, and they're going to tell you, make claims like these. This toy here is going to increase your baby's cause and effect understanding. This toy here is going to also help your baby learn about cause and effect. All these marvelous toys. And what has always struck me about these toys is that they're a peculiar product of our age, because in 1970, no toys would have been marketed like this, right? You would have had the same kinds of baby toys. Of course, we call them basically rattles, right? Like you do something and it makes a noise. And they were widely available, but you wouldn't have talked about them as cause and effect understanding, because that wasn't the state of developmental theory at that time. Piaget had been very clear that infants were pre-causal, right? That they couldn't understand cause and effect reasoning. There was no point in giving a baby a toy that was about cause and effect reasoning, because babies had an undifferentiated sense of efficacy. They couldn't distinguish causes and effects. Causal knowledge was a late emerging abstract concept. And now, here in the 80s and 90s, we know babies are much smarter, right? Why were the babies confused in the 60s and 70s? In part because Piaget asked babies and children, even much older children, to explain complex events like how a bicycle goes, why a river flows, and the kids gave pretty nonsensical explanations, or they attributed them to psychological principles. The river flows because it wants to, right? And he thought that he really well distinguished physical and psychological causality. By 1990, we made our children much smarter. Why? Because we actually have a lot of good knowledge that children do have, as Josh, I think, I've discussed extensively, core domains in which they have quite sophisticated theories and representations of the physical world that make distinct predictions from representations of the psychological world. So that's one piece. But there's also a particular piece on infancy, which is an interesting example of cases where you can actually maybe see causality. So let me talk about these a little bit. One contribution to the idea that babies really do represent quite specifically causal predictions about objects distinct from causal predictions about agents also comes from the Spelke's work. So I told you about a couple of the Spelke principles called continuity and solidity, but another really important principle about objects is contact causality. So if I want to pick up that coffee cup, I could feed with it and talk to it and do all kinds of things, and that coffee cup is going to stay right where it is. But if I would like Josh to move, I can say, Josh, can you please get up and close the eyes? Right? So I can act on Josh at a distance, but I can't act on that coffee cup at a distance. We take that, again, that's just common sense, right? Of course that's true. Objects refer to contact causality, but it seems that babies have these expectations too. If you give them an object that is ambiguous, maybe it's an object, maybe it's an agent. If you give it other cues, independent cues to agency, and we're going to talk a lot about cues to agency, but if they know this thing moves spontaneously by itself, or if you give it morphological features like eyes and a face, then they expect that an object can both resist being moved and move itself and move other things. But if you don't give them those cues, then babies expect that objects obligatorily move when hit with requisite force, that way. So they're interested to be able to resist motion, and they are surprised if it moves by itself when there was no contact causality. Again, it's work by an AI. So these things together, by the way, Liz Spelke has actually given her name, essentially, the field has adopted it on her behalf, for what an object really is to a baby. It's a Spelke object. And to say something is a Spelke object is to say that it respects these three principles, right? And that's essentially a plausibly innate, plausibly phylogenetically broad representation, abstract representation, because it holds for all objects, right? And it holds on first sight. You can make predictions about what's communicated for objects. Let's talk a little bit about this perceptual causality. All of our marketers now love how you causal reasoning is a very easy problem, although children maybe need some help with all these toys to really master it. But some of our greatest philosophers have thought of causality as a really hard problem. And one of the reasons they thought it was a hard problem is that you just see one thing after another, right? You don't actually get to see causality in the world. It's, the naive realist view that you just sort of watch the billiard balls and you can see one cause another. With the Tennessee Hume disputed, you just see one billiard ball moving and the other. You don't see the necessary connection. You don't see what makes that a causal. Interestingly, work by an adult cognitive scientist, Michottean, suggested that Hume may be right in principle that you should be able to see it, but in fact, the perceptual properties of certain displays seem to give rise to a representation of causality that is extremely sensitive to particular spatiotemporal parameters. And if you manipulate them even slightly, the perception of causality goes away, and if you have them very stably, the perception of causality is robust, and adults report it. And interestingly, they report it even actually when they know causality isn't present. For instance, when Michottean was doing it, he didn't have animation software. He just was able to use the equivalent of flip books that you make, right, with paper and pencil. And he had what looked like, black balls hitting one another on a screen. And if the one ball came in and directly hadn't moved another ball, adults reported it as causal. So this is a crude illustration. I apologize, but something like that, right? And they said, well, then it looks like the blue ball is moving the green ball. Call that a launching event. But change that ever so slightly by putting, for instance, a spatial gap between the two balls, and adults no longer report causality, they report two independent events. Put a sufficient temporal delay in, and adults report those events. Okay, so it looks like actually under some conditions, we are motivated to see causality in the world. What about babies, right? Do they just see these as one event next to the other? Do we learn that these balls cause them, or do we get this as even when we're infants? That's a hard question to ask a baby, right? How do you ask them if they see a direct launching event as causal, but a spatial gap event or a temporal gap event as non-causal? Alan Leslie came up with what I think is a rather ingenious solution. He said, well, let's show babies each of these events forward, right? Blue ball hits green ball either directly or with a spatial gap or a temporal gap. And then, after they're bored with that, let's play all these events backwards. And what he said is, look, in all of these cases, lots of things change, right? You're reversing the trajectory, you're reversing the time of these events. That's true across these events. But only in the causal events are you reversing the agent-patient relationship. Only in the causal events is the thing that was bonked because of the bonker, right? If babies understand that event as causal, it's not just a change in space, it's not just a change in timing or trajectory, it's a deep change in the structure of that event. First the blue ball made the green ball, now the green ball makes the blue ball. If babies are indifferent to it, then all of these events should be equally interesting. The reversal of each of these events should be equally interesting, but if they care about the causal structure, a much deeper violation happens when you reverse the causal events than the other events, and that is exactly what he and very many other people have done. Starting at 6 months of simple events, babies distinguish causal and non-causal motion events. They seem to assign these balls the role of agent dictation. And as I say, we now have some good evidence that newborn chicks do this thing. Okay. That's a whirlwind for causality. We're going to talk a lot more about causality when we actually talk about learning and representation. Yeah?
Actually, a main question, but
Sure.
why doesn't it happen early? I mean, at an earlier age, because, for example, they understand that very early that if they're hungry and they're given food, they will not be hungry afterwards. And that happens, I mean, I know that, I suppose that some babies might, it takes time for them to make this connection, but after, I don't know, a month, they understand it. So,
one of the things that we know is phylogenetically brought, right, is the ability to form associations between events. And actually, there's two sets of abilities that we know happen in any organism we might be interested in testing, right? All animals can draw predictions after repeated pairings of events. Right, so A happens, then B happens. If A happens, they will learn to expect B. Depending on the intelligence of the organism and the stimuli, you may have to vary the number of trials. But if A repeatedly predicts B, most animals can learn that A predicts B. So that's classical conditioning, right? And all animals also can do operant learning. If they themselves do something and something happens, right? They push this button, they get apple juice, and they get fed. They push this button, and they get shocked. They quickly learn the association between their own action and the world and what happens to them. What we strikingly don't have a lot of evidence from in the animal literature is the ability to bridge this gap, right? So animals can repeatedly, for instance, hear a tone and receive food, right? And they will even make different predictions about the events they see in the world and events they intervene on. But what they do is, having heard a tone and gotten food, and then, say, learning how to activate the tone, they don't actually design an intervention that say, oh, if I do this, I'm going to be able to get the food. They don't go from observing this to imputing a causal connection for it. We don't have good evidence for their ability to bridge that kind of gap. What you're seeing here in the babies is the ability to represent what might just be an association. In all these cases, green ball moves and blue ball moves, and represent something richer about it, represent a causal and structured connection, even though they're not directly involved in the event, even though there's no instrumental conditioning happening. Is that correct? Okay. Let's move a little bit out of the physical world and move to the world of agents. So, I'll just ask this little question. You've just traveled to another planet. Scientists now tell us that there are all kinds of planets out there that might be supporting intelligent life, so we shouldn't limit our discussion of intelligence parochially taught us earthlings. How are you going to recognize agents on that planet? What are you going to do? Anything here? Yes.
See the things which appear to be acting on other things.
Okay, so you might look at things that are acting on other things. What else are you going to do? First, the wind acts on leaves. You could be mistaken, rocks rolling downhill acts on other things, but maybe it's an agent. What else is a cue to agency?
Go interact with it.
Well, interact with you. Right? So when you go there, does it run away? Right? Or does it attack you? That would be a good cue. What else? Yeah.
Does it change information to the environment?
Okay, is it adapting to its environment? Is it moving in these ways that we want to talk about? I think if we're going to talk about what we mean by intelligence, there's some of the questions we want to get at. What kind of behavior would recognizably cue us to an unfamiliar organism that it was behaving in any kind of intelligent way? And although this is sort of a silly hypothetical question when you think about going to another planet, it is arguably the kind of question you were all presented with when you came into this world, right? Here you are, first time. How are you going to recognize the agents, right? Who out there is an agent? How do you distinguish them from the objects out there in your world? Sorry, question? So we've considered a lot of different and there's a flip side of this question. Suppose you showed that babies were sensitive, say, to objects that acted on other objects. They were sensitive to objects that responded differently to themselves. They were sensitive to objects that adapted in various ways to the environment. Would you think they had a contingent agency? Would you think they had an intuitive psychology? Would that be sufficient for you to credit an infant with that kind of representation? And people have been interested in both sides of this much. To give you a sense of why this problem, again, part of my goal here is to just break apart common sense a little bit. It seems so trivial. Of course you can recognize agents. Look around. You see, some 50 of them sitting in this room, and they're very clearly distinguished from the object. But you could see the world otherwise, right? So here's a little thought experiment. What you really see are bags of skin stuffed into pieces of cloth, draped over chairs. There are small restless black spots that move at the top of the bag of skin, a hole underneath that irregularly makes noises, bags move in unpredictable ways, etc., etc. This is a description by Alice Gopnik, trying to imagine what the world might look like if you were genuinely mind blind, as people have sometimes proposed as a characteristic of autism, right? If you really didn't see the internal life, if I didn't see you as having goals, intentions, beliefs, desires, internal representation, this is what I see, right? And that would be a scary and alarming world to live in, but it's certainly possible, right? It's not given to me that I get agency into the psychology for free. So how do you get it? Well, one thing is the basic ontological distinction. One of the first is here, as we'll discuss. Arguably one of the last to go. There's been a little bit of work on Alzheimer's patients, because long after a lot of basic category distinctions drop out, like the ability to distinguish dogs from planes, there's still the ability to distinguish dogs from cats. There's still a distinction between agents and objects. How do you do it? Well, one of the things that makes it challenging is, of course, all agents are also objects, right? So you are also a Spelke object. You often move continuously through space. You don't pop in and out of existence. You can go through walls, and you have a lot of superficial properties of objects. And so you have to rely on these other kinds of cues. For humans, of course, we get all these morphological cues. A lot of you and a lot of other things have faces. I'm not going to spend a lot of time on faces. I think you'll probably get a lot about faces in the course of discussing intelligence in various ways. I'm going to talk more about these dynamic and functional cues today. Premack and Premack were comparative ethologists, and they suggested that, one of the clear cues to agency is spontaneous movement. They suggested even snakes are sensitive to this kind of thing. They'll freeze if something moves spontaneously in the environment, and that may just be a perceptual trigger. And it supports the basic, again, ontological representation that you might think is quite common to them, because for all kinds of animals to recognize agents out there in the environment. We know that spontaneous movement is important. It's often an issue to move is important to basic core representations. As I said, physical objects with contact, they allow animate agents to resist it. And I think some lovely work demonstrating this comes from Rebecca Sachs in the department who also hear from on Friday. She sent a beanbag flying over a wall, and it landed right there. And all you get to see here is actually an object. But the object is behaving in a not very object way. It appears to be moving spontaneously. So if you resist that notion for objects, right, then you have to believe that something moves that object. And that something is probably an agent. And so she showed babies, after they see a beanbag fly over a wall, a hand, and the hand either moves with the origin of movement, it appears on this side, or the hand appears on this side. And the argument is, you might expect an agent on this side, right? Because something has to be responsible for the spontaneous movement of the object, and it should be an agent. But you have no reason to expect a hand over here. This should be surprising. That should be less so. And indeed, babies look longer at this hand than at this hand. And they only look longer if it was a hand. If it was a train, another object that moved out there, the babies showed no looking time distinction. Moreover, you might say, oh, look, hands are very familiar, but babies actually see hands during objects. Is it something, and also hands actually can for objects, so the right mechanical affordances to do exactly that. But if you really care about the basic ontological distinction, the fact that there's a kind of thing that can initiate movement in the world, then you might have a much more abstract representation and expectation. What if I don't give you something familiar? What if I don't even give you something with hands and the right affordances? I just give you something with other cues to agency, like those morphological cues, like, for instance, a face. Well, it so happens, if this little guy here, who they've never seen before, and who doesn't have hands, but who can move spontaneously itself, and who does have a face, babies treat it like a hand and not like a train. They expect it over here, and they look longer when it appears over here than when it appears over here.
How old?
The original results were in 10 to 12-month-old babies, and I'm never very good at ages. I think she might have gotten a little younger, and if anyone knows, tell me.
It might have gotten down to 7 months old.
I think you were right. Or I will just assume you are right about that. More interestingly, if that guy itself is the one that jumps over the wall, the baby's no longer expecting that. Right? So what you see is this creature with eyes. And this creature with eyes, instead of the beanbag is over here, well, that creature with eyes, it can move spontaneously, it can do whatever it wants. And they don't expect that a hand initiated it.
So the train like, moved out?
The train moved out in exactly the same trajectory as the hand. So the argument, the control here is a low-level control for one thing emerged on this side, the beanbag, maybe they just expect other things to emerge from that side. And to show that wasn't true, that it was specific to the hand, if a train emerges from this side, it's just as surprising as if it emerges from this side. Yes?
What are the differences between the gauge times when it's expecting and not expecting?
Statistically significant, but I don't have the actual graphs up here. They look longer. You usually get two measures for midterm looking time, so how long on average they look at one display than the other, and how many individual babies show the looking time preference. Okay. Objects don't move by themselves, agents do. But is that sufficient for a baby to, again, if they had that cue, would you be satisfied that they attributed the naive psychology to agents, right, that they really understand everything about agents? There's some reason to think not. I'm going to show you parts of the study in pieces, because I think it's a really nice study from Susie Johnson's lab, where, again, we're going to use something beanbag light here. This is a fuzzy green blob, basically, and the blob has a little light up there, has a capacity to beep. In some conditions, it has a capacity to move, and in some conditions it has a face, and in some conditions it doesn't. And what she was interested in was what cues to agency supported other cues to agency. Right? So what would babies use? Do they have a whole coherent representation of this concept? If you show them one thing, do they expect other things of it? And so what she was interested in, what she was interested in this. We know by 9, 10 months of age, babies do something quite remarkable, which is they go like this. Now, I don't know if I managed to get a list of response from you, but I'm hoping that some of you are following my gaze out that window, right? Because I turned and suddenly looked in that direction. And if I pointed, I think you guys would follow my attention. You didn't do that when you were 6 or 7 months old. You did start doing that when you were about 9 or 10 months old. rule, which is to say, you didn't look at me, you didn't look at my finger, you looked where I was looking. You used my attention to gauge your attention. That's development called joint attention. It emerges towards the end of that first year, 9, 10 months. And what she wanted to know is, when would babies treat an entity as an appropriate subject of joint attention? When would they follow its gaze, right? So she had a fuzzy green blob who moved spontaneously, and the fuzzy green blob turned and oriented in a particular direction, and she wanted to know, will the babies turn and follow that entity's gaze? And spontaneous movement was not enough. And you may say, well, of course it's not enough. It doesn't have a face. What do you even mean to follow the gaze here? But as I will show you soon, you don't need a face to get babies to follow the gaze. But you do need more than spontaneous movement. So we're going to come back to that. So if it did move with the face in turn, babies would follow. They'd engage joint attention. But if it did exhibit spontaneous movement that didn't have the face or these other cues, babies didn't treat it as an agent with respect to each other. Okay. Well, maybe you need a little bit more than spontaneous movement. As noted, if you went to another planet and looked for things that spontaneously moved, you could be very distracted by whatever the, other kinds of physical forces, perhaps unfamiliar ones, were causing things to move about on that planet. There's this powerful magnetic field in lots of things are moving about, but that's the magnetic properties, not because of their psychological ones. So somebody mentioned, well, you really want to see if they adapt to their environments. Most of our objects don't. We're designing a few that do, but by and large, objects don't do that. And so infants might use all of these things. Once they understand that objects do exhibit properties of inertia, then they might use violations to say that that has self-generated movement, that is something like an agent. And I think the nicest work on this comes from Gao's lab, where you can see that subtle cues to changes in the motion trajectory, and in particular, heading makes a big difference to the representation of agency. So I can move around this room in a lot of ways, and you're going to take it to be an agent. But one thing I don't usually do is move like this, right? I move in the direction of my head. I don't just move about in all kinds of other directions. And it turns out that that heading and the ability to follow and change with speed, work really matters to the structure of agency.
Top right.
I'm sorry?
Top right. Run this time.
Excellent. All right, so what do you guys see here? Anyone?
A bunch of airplanes looking at a ball.
Bunch of airplanes looking at a ball?
The green is running away.
Yeah, anyone want to be that green ball right now? No. That green ball looks like it's being pursued, right? It's being chased, harassed, carried. Tao refers to it as a wolf pack effect. What I want to show you is how quickly you can make that go away. So everything is the same here, except that the objects are no longer following a fixed orientation and fixed end, right? And absent that, you see something that people describe often more like snowflakes or a jumble or just physical objects, right? So a lot of our perception of agency, like our perception of causality, appears to us on relatively subtle spatial parameters. And you can show that this is true in infants too. I don't have a video of that often, but babies are also sensitive to cues like changes in stop and start and in trajectory and in heading. I think though that a more interesting one on cue to agency is this business about contingent behavior. So someone mentioned that one way you could go to a planet and find out what the agents were is the way they respond to cues, right? If they ran away from you, if they attacked you, if they tried to make contact and trade things with you, you might be inclined to think they were agents. And so Susie Johnson tried this as well. She had that fuzzy green blob there, and then babies tend to do things, spontaneously. They go, ugh, and the bob went, beep, beep, beep. And the baby would go, whoa. And the bob would go, beep, beep, beep. And then the baby would move its hand, and the bob would go, beep, 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 beep. So it was responses were cued to the baby's own action in one condition. In the other condition, the babies got the behavior, the green blob behavior of the previous baby, right? So they're seeing exactly the same evidence that's no longer contingent on that baby's own behavior. So in one case, the baby's getting lots of contingent responding. In the other case, they're getting exactly the same kinds of beeps and flashes, but it's no longer contingent. Now the green bob goes out of phase, goes ahead and orients to a certain direction, and in the contingent condition, the baby follows its gaze, and in the contingent condition where there was no contingency, the baby dips. So they seem to treat that as, again, a cue to agency, again, even absent morphological cues, even given that those objects move spontaneously.
Are there any experiments that show that this is just contingency in general as opposed to contingency to the baby's own actions?
Well, she did an interesting follow-up. You might wonder how this thing, we kind of think this is the head, right? But it's possible this is the head, right? How do you know? It doesn't really have a face. It could have a really big head and a very small body, or it could have a small head and a very big body. And that's a little problem when the thing goes diagonally, right? Because do you face this way because the little head is that way, or do you face that way because that's the tail and the head is that way? And so Susie walked in and she tapped to the green blob in one position next to the baby or across from the baby, right? So one or the other was more plausibly the head of this object, and that's the third party interaction, and the baby is selectively oriented to the direction in which she spoke to the heavy green blob. Okay, so they determined the heading by the direction of the apparent communication. So these are fairly sparse cues to agency here. Again, you have a fuzzy green blob that is beeping and flashing its lights. And yet, in one condition, they seem to be interested in what the blob is looking at. They orient their own attention accordingly. In the other case, they don't. Okay. So, by quite early in development, and discriminate many characteristic features of agents and objects based on these dynamic cues, and also based on some of these functional cues. But again, we might want to know when babies bind all of these features together. And in particular, not just when they predict one cue off another cue off of another cue, but when we can really decide that these features cue the things we can't see and we can't observe. The fact that you are hanging out there not just with changes in trajectory and contingent responding and behavior, but with an inner life, right, with goals, with intention, with nothing. So goals are, I think, a precursor. Understanding the agents of goals is a precursor to theory of mind reasoning. I think you'll hear a lot more about theory of mind reasoning from Rebecca, hopefully on Friday, and I think from Josh shortly. But today I'm just going to sort of walk into what you would need even to get there, right? So there are behaviors that can be exhibited by both objects and agents that aren't about anything. A rock rolling downhill is not about anything, but me rolling downhill if I trip is also not about anything. I'm an agent doing it, but I'm acting qua object in that case. If it's an accidental action if I trip, it's not a reflection of my inner mental state. Intentional action is about things in the world. It's either goal-directed or referential. And I think the simplest example I'm using in the MIT classroom when I talk about this, but if I wave my hands around vigorously in a classroom, my action is either functional, I'm trying to make the lights turn on, or I'm trying to do something communicative and referential. These are the stupid lights that tend to go out when you're like, having a quiet moment in the lecture. So when do babies appreciate these aspects of action, the aboutness of intentional action? Ever used one of these before? No, not very good. Okay. So understand this is not a full theory, right? I could infer the action aims at an end state without deciding that you want to do that. I could decide that you're referring to something without really fully saying that you think or believe. But if you're going to get mental states like desire and belief, you're at least going to have to see action in the case of intentional agents as about things. So this is a prerequisite to a full-fledged theory of mind. You might want to know when to use it. So I'm going to start with a classic video that I assume, have you guys all seen it? Well, if you haven't, allow me to introduce you to Pixar circa 1944. I feel the tension. All right. Can you describe for me what it is that you just saw it?
Kids harassing an adult.
Kids harassing a bully. What else?
Big triangle defending his castle.
Big triangle defending his castle. Get a couple more. Third class here. What else? Yeah.
Two friends were playing, then they were assaulted by something.
Two friends was what?
Were playing, then they were assaulted by someone.
Two friends were playing with were falses. Right. All right. And many of you are privately imagining much richer narratives here, right? Which you're embarrassed to say because part of you is thinking, no, come on, just come triangle, circle. Let's not carried away with, this story of, romantic love and the big, jealous Billy and blah, 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 blah. But undergraduates are much more forthcoming, and they'll tell you all these stories. Right? And they're telling you that from, in fact, triangle. And that's remarkable and strange, right? And you should be puzzled by it. And it is a problem for intelligence. When we say common sense reasoning is a hard problem, I think more than anything, we mean this. This is a very old demonstration, right? From quite sparse data, from motion trajectories, from relations, and from a lot of rich, structured internal representations, you're telling a story that goes far beyond the essence, far beyond the data. And yet all of you saw it, and all of you saw it effortlessly. And if I showed it to children, they would tell you stories like this, bullying and castles. They would feel fear, they would giggle, they would be delighted at the happy ending. And one question you might want to ask is, what about infants? You might say, okay, well, look, you can do that to me because I grew up in Texas, right? Like, I've grown up in a world where I've never been free from cartoons. I've been taught this all my life. What about babies? Some lovely work by some Hungarian development psychologists in the 90s started asking questions about what babies could perceive from simple goal-directed. They habituated babies to events like this. This looks like a very mean sketch, but it was a very dramatic moment, especially if you're a baby. What you have over here is a small ball. What you have over here is a big ball. But what you see is the small ball backing up and back and forth and doing a little contingent responding thing, beep, beep, right, and flashing, and the big ball over here saying, beep, 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 right, and the small goes, beep, beep, and the big ball, beep, 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 right? And irresistibly, you have a baby ball who is separated from a mama ball, right? That would seem to the adult projection, but what do the babies really think? Well, what you see is you see the baby ball back up and jump over the obstacle to get them out, right? I'm going to continue to use ancient terms here, but I think it's justified, as you will see. They see that over and over again, but of course, really what they just see is a ball, some beats, and a trajectory through space, again and again and again. They are bored. And then you show them either the old action, which they have just been bored by, but which is now strange. Because the agent has a goal, and it's a rational actor, which is to say, it's acting efficiently, it's trying to take the shortest path towards its goal. Then the ball will go like this. This is a new action. The babies have never seen the ball go like that. But that is a rational action if you consider that as being a goal-directed action. If you just consider the trajectories in space, this is familiar action. This is what they've seen the ball doing over and over again. This ought to be boring. That ought to be relatively interesting and new. But you ought to get the flip if you're making that mistake or goal-directed inferences about it. And what you are seeing here is that infants do this. They do it at 6. This is not a great representation, but 6, 9, and 12 months of age. The biggest version, 6-month-olds who live the longest, the 9-month-olds and the 12-month-olds. Not only do babies infer the action, the relevant action, as the environmental constraints change, they do it quite selectively, because you just put the wall behind here where it's no longer a goal in the first place, and the ball is always exhibiting an inefficient action. The babies have no expectation. And if you show the babies the action itself, but there's an occluder up, there's a screen, so they can't see what's behind here. By 12 months of age, babies will posit an obstacle they've never seen. So they are more surprised if no obstacle is present than if an obstacle is present. Although they never saw the obstacle, they have to invent it and treat it to make sense of the action. So again, this is in pre-verbal babies, for our verbal. So we know babies are sensitive to other agents' actions and goals. They see something like what you see perhaps in these many higher and simple videos. And as you'll see in a minute, even quite richer indications. But let's talk about some of the earliest and I think most straightforwardly compelling research suggesting that babies see agent actions as goal-directed. Amanda Woodward showed babies a reach, right? And there were two objects, and the hand reached for one of the two. Let's play the ball repeatedly. Ball, 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 ball. And then the hand easy just switched the position of the object. Another hand's doing exactly the same thing, right? Continuing to reach in exactly the same place, but now there's a new goal. Or the hand exhibits an entirely new reach, but for the same goal. Now, babies care primarily about the low-level surface features of this action. They're primarily sensitive to just the change in trajectory, then this event should be more interesting than that event. But if they make attributions about goals, and what they care about with agent action is goals, then you ought to see the reverse. This action, although superficially familiar, is much more interesting. This action, although superficially novel, retains the goal much less. And in fact, 6-month-olds showed exactly that result when it was a hand, but not when it was a mechanical ball. More interestingly, 3-month-olds didn't care at all. Right? 3-month-olds did not seem to treat the goal as an important component of the agent action. And one hypothesis is that it's because 3-month-olds themselves have never sufficiently reached for anything at all. Right? You have a 3-month-old, they hang around, they flail, occasionally they happen to whack things, but they're incapable of executing a controlled reach. So Jessica Somerville took 3-month-old babies and she put Velcro mittens on them. And now the babies were given a few minutes for the first time in their little lives, and the first time in the history of the world, in successfully reaching for objects. 3-month-olds suddenly reached out and were able to entrain and pick up an object, and that was a brand new event for babies and for a small step for humanity. And they did that for a few minutes of playtime. And then they saw these same videos, and the babies who themselves had executed a reach now made the distinction, like the 6-month-old babies, they looked longer at the change in the goals and in the change of the trajectory. The 3-month-olds who did not have that training failed to make the distinction. The baby's ability to recognize his agent goals is arguably a little bit related to their own ability to act.
And that training was only for a few minutes?
Only for a few minutes. Because you try keeping sticky mittens with 3-month-old babies for any longer than that. Yeah.
And they still show no interest in the claw.
And they still, right, it's a distinction. Actually, that is an excellent question. Do I know that they ran the claw control? I do not. Let's talk now about some recent research that I think has once again upended our understanding of sophistication of baby representation. This is work by Heisen Hamlin. I'm going to show you the first groundbreaking paper here, but she now has literally some 20 studies testing different dimensions of this experiment. It is one thing to understand the goal, to reach for an object, to go over a wall, but one of the really interesting things about human action is that my goals can be your goals, which is to say, I can help you. If I know what your goals are, my goal can be to facilitate your goal. Or it could be not finished. My goal could be for your goal, right? So if I can represent your goals, and if babies understand one agent's ability to take on another agent's goal, for better or for worse, then they should be able to represent action not just as goal-directed, but as potentially helpful or as hindering. And so I want to show you a few clips suggesting that infants can do this. Oops, that's a very small clip. You guys see? I think I can make it any bigger here. What you see is a very small red ball trying to get up a hill, and that is a little yellow triangle. And what you all see is that they are trying to help that guy up and down, right? So that's a little helping video. Here, it would be an example of a not so helpful agent. I hope. Show that again. Okay. Well, you can imagine the scenario. I can't actually get it to play. I'll just play this one again and we'll see what happens. Red guy tries to go up, and this time, instead of coming behind and helping the guy go up, what you see is a blue square who comes from the other side and tries to push the agent again. Okay? Having seen both the helping and the hindering events, you can then show the baby an event where this red guy has to make a choice. And in one condition, he does what you might expect. He approaches the helpful agent, and in the other condition, he does what you might not expect, which is he goes ahead and he approaches the hindering agent. Everyone clear on that? Now, I've just given you a nice narrative explaining it, but of course the babies don't get a nice narrative. They're just watching these simple events. And of course, they form any expectations based on the behavior that they've seen here about what that agent is likely to do and who that agent is likely to affiliate with. And of course, the striking answer is that they expect the agent to approach the helper and not to approach the hinderer. It matters that that thing is an agent. If it doesn't have eyes and it's an agent, babies have no expectations about the approach. And you might say you could get that effect if the babies are only sensitive to helping and think agents should prefer helpers, or if they're only sensitive to hindering, and if they just think you should disprefer agents who block you. She also did an experiment where she compared helping and hindering respectively to a neutral agent. Where the agent just was bystander, just watched what was happening. And the prediction in this case is, of course, that babies should expect you to approach the helper over the neutral agent, but the neutral agent over the hinderer, and that's the prediction. Is that okay? So this is actually just a summary of what I just showed you here in the agent condition and the object condition. And when you're comparing with the neutral, she found this effect with both 6-month-old and 10-month-old, and later results for the infants are looking. She's shown that result as young as 3-month-old, and as Josh will show you shortly, she can show not just these kinds of preferences, but these preferences are predicated in actually knowing what the other agent's goals are. You have to understand what that agent wants to do. This is a remarkable set of early representations for babies, a fairly rich, sophisticated set of structured representation about the nature of goals. But again, doesn't reach the level or need to reach the level in these experiments of a full, the ones I've shown you, of a full theory of mind. But we have increasing reason to suspect that a lot of the even richer representations may be coming very early. Questions? We'll see some of that later. Yeah.
This is again, it's an experimental question. How do you tell maybe says, oh yes, I expect this or not? What is there like a certain sound they make or?
No. You're right. In this case, they're looking. So she's done it in a variety of ways. She's done it with looking time, but she's also done it with the children themselves. You bring out the two objects, and the babies at 6 and 10 months, 12 months can reach, right? So you just let them, the experimenter who comes and presents the stimuli is blind to what the baby's just seen. Both objects are there. The baby gets to make a choice. And the question is, do they selectively pick up the helper over the hinderer or the neutral agent? Do they selectively avoid the hinderer over the helper and the neutral agent? And you can see babies doing all of these. Yeah.
I couldn't see in the video, but these agents don't have any sort of eyes or...
They do. In fact, it's important that they have eyes, and it's important that their eyes exhibit a heading that they actually move in the trajectory of motion. She does them without eyes, and you don't get these effects. So it's important that they're encoded as agents, the kinds of things for whom goals might be relevant. Yes?
So you said goals were a precursor to the theory of life?
At least babies have to understand it. Certainly, if they're going to understand that goals depend on your representations of the world, your beliefs, not just the way the world really is, you at least have to understand it.
What are some other things you think they have to represent?
I think that, again, I think you'll see some of this even later today, but what you really want to know, the arguments for that theory of mind, try to come down to understanding the mind is representational, right? It doesn't just copy the world as it really is. It is a representation of the world, and not that it can be lost, right? It's a belief about the world that you might lack knowledge, you might be misleading knowledge. There are a lot of ways in which this representation could be absent. If you really want to say that you understand the mind as representational, you would want to show that all of those are. In terms of, what kinds of things are prerequisites, I'm hoping to illustrate a lot of things that you might think might need to be in place, like the ability to distinguish objects from agents, the ability to have different causal expectations of how objects and agents will behave across a whole bunch of tasks, and certainly the ability to understand that agent action is intentional and has these properties differing in the world. Once you have all of that, then you can start asking what you understand about the nature of knowledge and about the nature of representation. Yes?
Do we know if adults seeing similar kinds of things show like saccade preferences that are similar to kind of the way babies look? Was there originally like a set of literature that kind of showed that the responses between both are similar and that adults...
That's a complicated question, right? So in general, there's a complicated question in development about how you get a common dependent measure that tracks across all of your different ages. So if I want to know what you see, I can just ask you. Right, I know you sort of bother to measure your differential looking reporting, and also you can capture information very quickly. So I'm not sure that we get enough variability from your looking behavior to get differential representation from a lot of stimuli that babies might look. So you saw, I think on that earlier Gerges study, how quickly the looking time drops off between 6, 9, and 12 months of age, where you get a difference between the 12-month-olds looking to the two events, but already their looking is like a third of what it was at 6 months. And by the time you get to adults, you get all of this in a glance, right? So you end up with different measures when you're trying to ask adults about what happens. But it is important in the infant literature, and people worked hard to figure out what can you do besides looking. And in Kyler's case, she does a lot of just choice, right? Like which agent you want to research into. Yes?
I have a slightly weird question about agency. Do you have an idea when children come to know that, or come to realize that adults up until then have really been screwing with them and assigning agency to objects that really never had it, like Mr. Phone and like stuff?
How often have you sworn at your computer? I feel like...
I never expected to respond, though.
What?
I never expected to respond, though.
It's an interesting question. So you could... People have long asked sort of the question, like, we think we're screwing with them because we represent things fancifully, or we, do this. And it turns out kids are exquisitely good at distinguishing pretend scenarios from real scenarios.
Even when they're doing these tasks?
Very early.
So they don't really think that the agents are agents, they just think that the adults are calling them agents because they're in this game?
Again, you're in trouble when you start trying to, for any experiment which you don't have the data bearing on it, say what's going on in the inner life of the baby. But lots of people have thought about the problem of these fictive representations, right? So it's a problem for adults no less than children. Philosophers argue a lot. You go to the movies, right? You have rich emotional reactions to those. You can get scared by a thriller. You can get moved, by things that you see on the scene, but you don't call the cops, right? You don't actually confuse it. And yet you have a lot of reactions that are quite specific to the representation agency, including real emotional after effects and, real discussions about what went on these totally fictional characters. As far as we can tell, babies are perfectly good at working with symbolic representations, working with cartoon depictions, working with visual symbols, making attributions about them, but without confusing them. right, with XD humans. Starting at 12 months, babies will pick up a block and go vroom, 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 right? So they can represent that block as standing into a car. You get these stand-in symbolic pretend representations very early, and they don't seem to be confused, but I think that those are some of the hardest. Like, I'm showing you stuff we do understand. If you want to start asking me about imagination or representation and the status of these things, we're in a world of hurt, because it's a really, really complicated problem. It is what kids spend a lot of their early childhood doing. It is uniquely human as far as we know, and we don't understand what roles it plays, or the real nature of those kinds of representations. So with that, let me turn a little bit to learning, which I'm just going to preface here. And to do this, I'm just going to talk a little bit about what you might think, how you might think learning works reasonably, because there's been a couple of major traditions that have been hugely influential. One is the Piagetian tradition. I alluded to Piaget. I haven't talked very much about him, but if you knew a tiny bit about cognitive development, you would know Piagetian theory. And Piagetian theory was fundamentally a stage theory. Babies started sensory motor learners. Gradually, their ability to represent the world got more and more and more abstract, but fully abstract representation was a late development in adolescence, right? So, and a lot of early abilities were not present, and you thought there were these discrete stages. All of this research I've shown you has basically marked the demise of Piagetian theory. We now think there is no point when infants are only sensory motor learners. We think there is no point when abstract representations are not present. There is no evidence for huge stage shifts in cognitive representations for development. So that whole theory has collapsed. That's not to say Piaget has collapsed. He carved out the domains, like I say, from morality to probabilities, that we should be considering representations over. And he posited a lot of ideas about how you would bridge these gaps I'm going to talk about between experience and structured representation. But stage theory in particular has some. Another, of course, dominant theory of learning until the cognitive revolution is, and a theory that's been hugely influential and continues to be in neuroscience today, is just associative learning theory. How do you learn? You pair associations together, right? And kind of a famous quote in early developmental psychology is this one. You know, give me a dozen healthy infants, and I'll guarantee I can make them anything you want just by manipulating their environment, right? What governs learning? Environmental constraints, what you can associate in the environment. I can become a doctor, a lawyer, even a beggarman, or a thief. And a lot of things contributed to the collapse of behaviorism. But it was a very compelling theory and remains so again in their domain because it's incredibly measurable, right? You really can manipulate different kinds of cues in the environment and direct the behavior of rats today and mice today and neurons to a very big extent today. Just by controlling variations in the environment. But Piaget, among many others, said this is a problem. To explain these successive generalizations by simple associations explains nothing at all, because the problem is precisely to know why these associations are formed and not others among the infinity of combinations possible. So along with things like Tolman's experiments showing that rats learn things for which they were never reinforced. They learn the entire maze, not just the reinforced circuit. Along with Chomsky's argument about the poverty of stimulus, and that there was neither empirical evidence nor any computational way where you could get language from simple associations between words and things. And along with Turing, who showed actually you can make rigorous, measurable, quantifiable things that have nothing to do with associative learning, and yet are capable of rich informational processing, and that would be a program. All of these things together, along with Piagetian theory, suggested that behaviorism wasn't the way to go. You were going to need to consider mental representations. You were going to need to consider early structure. But just in case you aren't quite persuaded of this, and you aren't persuaded that common sense really is a hard problem and that there are an infinite number of possible combinations, let me give you a little multiple choice test here at the end. Speaker Pliny is going to point to this and say, GABA guy. So tell me, folks, what's a GABA guy? What does it mean? Don't overthink. A rabbit. Okay. Excellent. It might be a rabbit. And all of you are very likely to agree that it means a rabbit. But as the philosopher Klein pointed out, it could mean a rabbit plus grass. It could mean lunch. It could mean bugs. It could mean rabbits in the year 2014, but not thereafter. There are infinite things. It could mean animals, right? It could mean fuzzy thing, it could mean cute, it could mean bugs, right? How do you know, and how do you converge so rapidly, given all of these associations that are consistent with this evidence, on just exactly that one? Here's another example. Compare the sentence. The giraffe has a very long neck, or temper, or flight to Kenya. It seems totally trivial, and yet there are infinite combinations. You just read through one. The problem of common sense, again, completely tractable. I'll give you one more. What's behind the rectangle? I want to point out this problem that occurs in everything from linguistic structures to simple visual representations. What do you expect to see if I remove that yellow rectangle? A single red bar, exactly just like that. But it could be this, it could be this, it could be perhaps something you don't know, right? So you are jumping to these inductive generalizations. I think Josh spoke about this, and he's talking about shape bias, right? Why assume that you should generalize object categories by their shape? It's their texture, their color, their location, their time, any of the infinite properties they share. How do you either have or learn that that is the right inductive bias by which to constrain these infinite possible constraints? What is the structure that lets you learn rapidly from small amounts of data? That, I think, is the hard question that we're trying to get at. And this is a problem, like I say, from the motor learning system to language, vision, is from that cross-cut intelligence across all of these domains. Our instances are underdetermined by the data. If that is true, we need constraints on learning. I'll give you a last example about causal reasoning. Suppose I think actually I'm stealing this example from Tom and Josh. You didn't actually use it, did you? Yeah, from the Broad Institute. Suppose I tell you this research finding. Scientists came up with a technique for changing the gender of mice. They injected 100 mice with glucosin before impregnation. 70% of the newborns were male. Okay. If I ask you how to go to this as evidence for whether they actually succeeded in manipulating the gender of mice, you don't know. But can I see a show of hands if you might read the study?
What, sorry?
Read the study. They're all a cagey bunch. But now I'm going to tell you very similar data. ESP experts from the Institute of Noetic Sciences in Eugene, Oregon, my hometown is Oregon, or at least one I've lived in a long time, came up with a technique for changing coin flips. They flipped the coin 100 times, turning heads. 70% of the coin flips came up heads. How many are going to read the study? Okay. It's the same statistical data. What are you, incredibly biased and short-sighted? Right? That's elitist prejudice on your part, right? Your prior structured representations matter for how you interpret the evidence you have. And that's a problem I usually see all of this building, all of the loopholes. Also, there must be constraints on learning, and a lot of what developmental psychologists are given for that are the nature of those constraints. How many of them are hardwired and built in? What is the structure of those kinds of representations? How many of them learned? What are they? Should we expect those kinds of constraints to be? Okay. This posed a huge problem, right? A huge problem. This problem is probably for our graduate school, actually, which is this kind of chicken and egg problem. If you think about Piaget, but really, if you just kind of think about your intuitive theory of learning, like, well, how am I going to have a kind of abstract structured representation that's going to constrain my interpretation of the data? The only way I can get, I thought, an abstract representation is by getting a lot of specific examples, right? So I get this example, then I generalize, and I have an abstract theory, and I can use that then to make subsequent predictions and constrain the interpretation. But suppose, on a section of n, maybe this is not all of at once, but if I need to interpret those concrete examples through an abstract representation in the first place, how do I ever solve this problem? Why aren't I in a constant chicken and egg problem where I need abstract representations to constrain evidence that's otherwise underdetermined by the data, but I need the data to get that abstract representation in the first place? Some constraints, some of the ones I've shown you today, are plausibly innate. Maybe they inherit in our species and not the others. Maybe they're early developing. But surely not all of them. Not all of the things I use to interpret the world are we born with and are we just handed. So how do we solve that problem? And I think, a really lovely answer to that is the kind of answer that I think, I'm just going to good old black flag, the kind of answer that I think Josh talked about earlier this week, which is this idea of a blessing of abstraction. So I'm sure he mentioned it, I'll re-mention it once, which is this idea that you could, about a philosopher, Nelson Goodman, that imagine the problem of walking into a room where there are hundreds and hundreds of bags of marbles, brown bags though, so you don't know what's in them, but hundreds of them. And you go in and you open one bag and you pull out a blue marble. And then you pull out a second blue marble from that bag. And you move on to the next bag, you pull out a red marble and a second red marble. And the third bag, you pull out a green marble and a second green marble. Well, now you've seen 6 marbles, and there are hundreds of thousands of marbles in this room, right? But from 6 marbles, you can already make a pretty powerful guess that these bags are homogeneous, right? And that means that a single marble from each of the next bags will tell you what's in that bag, right? So you already know something about the abstract structure, and you know it from very little data, right? So you can use small amounts of data to get abstract representations, which then constrain your interpretation of subsequent evidence. That could be wrong. It's small amounts of data. Maybe you got some weird sample in your 6 marbles, but probably you didn't, right? So the fallible inference, it can certainly be wrong. All of probabilistic inference can be wrong. But it's a good one, and if it's right, it will support rapid, rich, powerful learning. And that's the kind of mechanism that we talk about when we talk about the ability to form over-hypotheses, and what I think that's what I talked to you about as a blessing of abstraction. So one thing you might want to know is really directly, if you do something like that marble experiment in babies, can you show that they can draw inferences of this? So this is some work by Catherine Dewar and Beju, really testing basically Nelson Goodman's thought experiment. What babies see is they see you draw a bunch of circles from box 1, a bunch of squares from box 2, a bunch of triangles from box 3. If you formed an over-hypothesis, you don't know what is in this, right? If you expect that whatever the first shape is, all the other objects that you pull are going to be the same shape, right? You can also flip this to color in a different position and form a different over-hypothesis. And so what she did was show an expected outcome, 1 red star and another blue star, or an unexpected outcome, 1 red star and a blue star, right? And if you've developed you don't know, right? You've only seen one thing pull it out of that box. But if you've already developed an expectation of what kind of thing it should be, then this should be a violation, and that should be expected. But it should be a violation only if it comes from this box. It shouldn't be something about just seeing 2 shapes that's more interesting than 2 different shapes than 2 of the same shapes. And to show that, if you pull that second blue circle out of this box, that shouldn't be a violation. That shouldn't be surprising. Because it's an over-hypothesis about the populations and the distribution of samples among the populations. And that's what babies are sensitive to. So they look longer at this and then this in experimental condition, but not in experimental condition.
I think we should probably...
All right, so that is, I think, actually the end of the talk. That's good. So thank you very much. Yes.
When you talked about babies learning something at like 6 months or 10 months or 12 months, what is the standard deviation on those numbers?
You're asking me the kind of question that I'm a bad developmental psychologist about. It varies from experiment to experiment. If you care about the precise ages, you'd have to go back to specific papers and specific questions. Sometimes the ages are really meaningful, like you really do show that an ability is present at this age but not at this age. But for very many experiments, what you find is that they've tested it in this age, but people just haven't looked to see if it's earlier. The absence of evidence for it earlier doesn't necessarily apply that ability is absent earlier, that only develops at that age. It's just that they ran the experiment on that age. Some of the reasons why you might run an experiment on one age and not another are irrelevant to the conceptual content of the experiment. You might run it because your dependent measure is reaching and younger babies can't reach, and you haven't figured out how to design the experiment without reaching the dependent measure. Or you might need to give the babies a fair amount of exposure to a kind of complex scene, and you just think you're going to lose the younger babies before you can even get to the interesting question. It doesn't mean they wouldn't have the ability if you could figure out a clever way to show it to them, but you haven't figured it out. So how much weight to put on particular ages and particular findings? There are some case studies where there's real precision and real care in those, but it really depends on which experiment you're talking about. You might be asking a different question, which is what age range do we mean? And the younger the age that you test, the narrower a range is permitted to be in a standard deviation of it. So if I'm testing preschoolers, I might mean from 48 months to 60 months. But if I'm testing 12-month-olds, I mean plus or minus 2 weeks. And if I say I'm testing a newborn, I mean plus or minus 3 days. Right, so there's a titration with the age of the baby, is what you mean. In infancy studies, if you say 6-month-olds, you mean plus or minus 2 weeks from their birthday. Other questions? Yeah.
In the study where you're drawing the Nelson-Goodman product steroid study, has people looked at when you are just drawing the balls blindly, or if the person's looking in and selectively choosing them?
Not in the overhead hypothesis study, but there's a really quite lovely studies about babies' expectations about the relationship between samples and population. They have shown that babies expect, say you have a box of red and white ping pong balls, there are more red balls than white balls. They expect the sample to resemble the population. If you are drawing blindly, if you're drawing selectively, all bets are off. If you're not drawing from the box but from your lap, all bets are off. So it is specific to sampling from the population. Babies care about the physical properties. If they know some of those balls are actually stuck to the wall and not available for sampling, then they constrain what they think the relevant population is, depending on the physical properties. Other questions? Yes.
So I think the handling study that you mentioned about like the helper, the hinderer, when we discussed it, we frame it in the moral understanding of it. But then I think that study is somewhat like the scarf can't really replicate it, because it's probably just a simple association between like the positive correlation and negative correlation. And then I think there's some problem with the scarf study at all. Basically, also like the googly eye seems to be like pointing downwards. So it's just like people can't keep record, and then it seems like a very debatable issue. So I just wonder, do infants have a good understanding of morality?
There's a lot in that question. I don't know the scarf study. What's scarf study?
I think it's kind of debated. I mean, yeah, the scarf was targeted on the handling study, and then there was a response from handling. They just keep going on and on. It was one of our topics in developmental seminar. So
Hamlin has come under a huge amount of heat for these studies, right, because it suggested very early abilities in babies. And you'll notice the title of that book is not about moral reasoning, it's about social evaluation. And I think that you've seen a slight shift in how Kylie herself talks about that work. She talks about social evaluation a little more than moral judgment because it got so much flack for moral judgment. But I think my assessment of the evidence is it overwhelmingly favors Hamlin's interpretation at this stage. There's a huge body of work, and Josh is going to show you some more, suggesting that these abilities are real and robust. Right? If you do control conditions where it's not an agent going up the hill, it's an object, if they're just associating the motion trajectories, you should show the same kind of phenomena. What I think you may have discussed in the class is, I think, an interesting point. There's some argument about the googly eyes, right? So like if they're looking like their goal versus they're just spinning in space. And the argument is that it needs to be represented as an agent and have that header. Right, you saw that effect yourself in looking at Taugao's Wolfpack studies, right, where you suddenly are like really seeing this as agency in one condition, and very similar stimuli, but with a different heading representation, no longer look like agency. I think it's a point in Kylie's favor that they represented as agency when it has a header, but not when the eyes are free to spin and it doesn't look agent-like anymore. So I don't think that's a content. Now, there's been some interesting arguments in the Spelke lab about whether you really want to take this in the full, rich interpretation of moral helping, or if it's something like goal congruence, or taking, literally, as I described, taking another agent's goals as your own, or understanding helping and hindering in a moral sense. For instance, you might want to wonder if you take someone's goals as your own, but their goal results in their destruction, right? You go up that hill and you're going to be blown up. If you have to have a moral sense, then the hinderer is a moral agent and the helper is not. So you could ask a lot of richer questions, but I think the evidence that babies do really distinguish agents who take on another agent's goals as their own, and versus hinder another agent's goals. They do it specifically in context of agency, specifically when they're causally implicated in the event. They do it specifically in context where the agent has reason to know what the agent's goals are. Is at this point overwhelming. It's replicated, I think, some 20 times. So anything can be wrong. Maybe it will fall apart, but I haven't seen any convincing evidence that convincingly undermines her interpretation. Yeah.
So in the object permanence experiments, so is the argument that what the object is that you no longer have that representation? Is that the claim of it?
That was Piaget's very old claim, which I think has been soundly disputed, right? So the old claim about object permanence is that babies, I always have to be careful when I teach this. When I teach this, so the undergrads actually put a big red X over it, because this is such an overlearned thing in so much part of the world. So if you take one thing away from you, babies have object representations. Object representations are innate and abstract. They represent hidden objects. It's not true that they don't have object permanence. Babies have object permanence. Whether they can reliably act on it in all conditions, the kind of performance constraints on acting on it and then searching for objects, clearly there are a lot of limitations on that. But there's no question, I think, about their ability to represent objects that are out of place. Again, newborn chicks can do it.
Right, so this is more of an attention span commitment. Like if you were to do the experiment that you showed with the with MR, if the frequency of that oscillation is low enough so that object will be gone long enough, will they just forget about it? Is that?
If they did, you wouldn't know how to interpret the results. I think it's one way to say, right? Like you can if an adult might not know what to think in that context, right? It becomes a little bit hard to say. So suppose I hide an object behind a screen, an hour elapses, and now that screen goes flat. Well, you may or may not think that object got moved in the interim or was still there. You may have forgotten about it because there were other things you were thinking about or not. But it wouldn't tell me. It would tell me much more about the other kinds of information processing demands on you than it would about your conceptual representation. So yes, you could mess with the phenomenon, but how richly you would want to interpret messing with it in that context, I think it would be very hard to interpret. Does that make sense?
Think about it more in that psychophysical sense. So what is the longest frequency, the slowest frequency that you can have and still have that phenomenon? I don't know if that'd be informative or not. Like if
I don't think anyone is, I think that's an important and interesting question. Like what's the whole psychophysics of these representations? What are the parameters on which they depend? I think that does matter. I mean, as we suggested for causality and for the perception of agency, small shifts in the spatial temporal parameters really can affect how you interpret that event. And I think it speaks to the kinds of percepts that give rise to certain kinds of representation. And that's an important question. I think it's orthogonal, the question of whether the conceptual representations are present, but it does ask, under what conditions do you, in fact, have those representations? And nobody, I think, has done it in full psychophysics of the exponent.
I'll talk a little bit about some of those kinds of things later on today, but those questions are part of what motivates sort of a probabilistic approach, right? To say, well, just like Laura was saying, right? Like your expectations about any of these aspects of object knowledge depend on general priors which can be graded about how the world works, right? Like when you say that objects are permanent, they don't blink out of existence, what you mean is all of them be equal. When you can't see this thing, you expect it's still going to be there. You can imagine, of course, various ways it could not be there. Like it could move out of the way, or somebody could move it, and those are going to interact with time. And I don't know if that's what you were asking about, but those are going to interact with time. The more time elapses, the more room you think there might be for other things to have come in to move that object out of the way. And I'll show you one example.
And that's the most beautiful single study. I'm not actually going to say
I'll show you an example of that kind of thing afterwards in a slightly different paradigm.
Yes. Yeah.
So in terms of the connection between agents and goals, seems like babies do a lot of things. Do the things that they do usually have a goal, or do they attribute goals to agents they see in general? Like, if you're talking about an agent could be something that spontaneously starts moving, does the baby assume that that spontaneous movement probably had a goal, or can there be just sort of spontaneous action without a clear goal?
Well, as So Susie had that experiment, right, where there were no other cues to agency, it moved spontaneously, and insofar as the dependent measure was drawing attention, the babies didn't treat it as having a goal, they didn't treat that as an intentional action. So there's lots of reason to think that just spontaneous movement by itself isn't quite enough. But again, if these instances are probabilistic and graded under some context with some type of prior knowledge or with some other cues to agency, they very well might treat it as potential agents. So in some context, a dark alone in the woods, spontaneous movement might be enough for me to, worry about agency, right? Again, I think if you think of these as graded representations where there are a lot of different things you might use,